Yes, so Katie and I both sort of actually invested in the idea of rehabilitating the Gibbs von Neumann entropy. And I'm kind of worried that my talk is not actually going to help with this program, is that I'm going to now make a bunch of suggestions that are going to make it sound very disreputable again, by attaching it to something actually a little bit more speculative. So obviously, as Katie said, the question here is that maybe the density matrix is real. When I first started getting involved in this issue, the key question was maybe the wave function is not real. Now it seems we've moved on completely. Now we're saying maybe the density matrix is real. And part of the motivation for thinking about this, as I stated, is, can this rehabilitate the von Neumann entropy as an objective microscopic entropy, something that's actually a feature of an individual system, an individual microscopic system. It's not something that's just applies to macroscopic systems. It's not something that's subjective or perspectival. Now, the worry I have about this is that just in itself, that's not going to help solve the error of time problem. It might make us be able to believe in the von Neumann entropy as a property of individual systems. But the problem of entropy increase, which is the really challenging problem for statistical mechanics, it doesn't seem that it's actually going to do a great deal of advancing that. So I'm going to briefly talk about that. And so then I'm going to start making more wilder proposals. I'm going to say, well, okay, in light of taking a similar kind of move, perhaps maybe wave function collapse to the solution to the measurement problem. If we have this problem, yes, there's a large body of literature looking around initial condition hypotheses and probabilities and so forth. But maybe a modest proposal is, let's just modify the dynamics some way. So what I'm actually going to be thinking about in this talk is whether or not density matrix realism opens up some new possibilities that simply aren't going to be possible without a serious form of density matrix realism. And this one generally is what Katie said is like a strong density matrix realism, where I'm going to be committing to the idea that systems, individual systems not entangled with any other systems, nevertheless are described by a density matrix as their ontic state. And that's going to allow different kinds of evolutions. I'm going to refer, for this talk, I'm going to call them row-ontic dynamics, a kind of non-unitary evolution that only makes sense in the context of density matrix realism. So obviously, there's various kinds of non-unitary evolutions that we can think about in terms of modifications to the Schrödinger equation that act on the level of pure states. The problem with those in this context always is the so-called non-linearity trap, is that whenever you turn this into a master equation that works on the density matrix, the result is linear, a linear dynamics, because the linearity is actually coming from the probabilities. So these will be a set and a kind of evolution that's only going to make sense when the density matrix is real. I'm going to try and look at what the consequences of those that is. And one of the straightforward consequences is that dynamics doesn't mesh well with much of the way in which we understand the solutions to the measurement problem in quantum mechanics. So I'm actually going to run through the sort of the classic trilemma of the measurement problem and say, well, how would this kind of row-ontic dynamics actually interact with these solutions to the measurement problem? And there's a challenge here, and it definitely, it's not immediately deadly to the program, but it means both programs actually have to be modified. So the kind of non-unitarity that row-ontic dynamics will give you is definitely a different kind of non-unitarity that would be helpful for resolving the measurement problem, which is really depressing and unfortunate. It would have been really nice if it had been the case that we'd actually just had one non-unitary dynamics and it would have solved both problems at once, and that would have been great, but no, it was not to be. So there's a tension between the solution to the two problems, and it's actually a question mark at the end, is actually whether or not a unification is actually possible. So at this point, it gets to the point where I'm more describing a technical program and where that might go and what prospects it has. So recapping on density matrices and entropy. So the motivation here is, for those of us, to attribute an entropy to an individual system, to be an objective property of that system, not of an ensemble or an assembly. It's not epistemic, it's not subjective, it's not perspectival. It's a full-blooded objective property of an individual system without, taking any prisoners. And if the density matrix is representation of an actual objective physical state of the individual system, then the Gibbs von Neumann entropy can become a candidate for such an entropy. And this is helpful. So I mean, I don't want to get sidetracked into a talk of the Gibbs versus the Boltzmann entropies, but it's certainly the case that for much of the practicing of physics, the practicing physics uses the von Neumann entropy as the entropy. I mean, I would happily give another hour-long talk arguing that that is correct and the von Neumann entropy ought to be the entropy that we consider the appropriate statistical mechanical entropy and not the Boltzmann entropy. But that's not the talk I'm going to be giving here. I'm just going to say, okay, well, the main reason perhaps why people are unhappy with the Gibbs von Neumann entropy is because this perception that it's not a property of an individual system. And you know, if we want, you know, the cup of coffee that I'm drinking to have a temperature, an individual temperature, if we want my cup of coffee I'm drinking to individually have its own thermodynamic properties, then entropy had better be a property of that individual cup of coffee. And under the standard way of thinking, at least, the Gibbs von Neumann entropy is not such a thing that can give an entropy to this individual cup of coffee right here. Okay. So to sort of recap, just to clarify what the suggestion here, so the sort of standard way of thinking might be that, you know, we have an epistemic, a proper mixture here, where these probabilities are actually some epistemic uncertainty as to what the actual pure state is. Can I just check? Can people actually see the hand pointer that I'm pointing? Good. Okay. So these probabilities are in some sense some kind of epistemic uncertainty, and the actual state is only one of these particular states. Now these states do not have to be an orthogonal set. So these states are not necessarily the states that diagonalize the density matrix. They can be a completely other set of states. So there's no sense of an ignorance interpretation of the states that diagonalize the density matrix here. Now that gives us this kind of epistemic entropy, but it seems to be, you know, the worry is this is subjective. This is actually based upon individuals' uncertainty or lack of knowledge. Well, maybe slightly better, moving in the direction of some of the things Katie was talking about, is if we have the improper mixture where we have a reduced density matrix. So we suppose that actually we're looking at a system that's just part of an entangled state with some other systems, and we trace out the other systems and we get a reduced density matrix. And it has exactly the same form, turns out, but now we have to interpret the values of P differently. We are interpreting them some actually properties of the individual system. And that's sort of okay. That's certainly better. I mean, there are some worries remaining though about this, because in the end we're still saying that the overall density matrix is a pure state. The overall Gibbs von Neumann entropy is 0. And the occurrence of entropy increases isn't something that's sort of happening globally. It's something that's happening locally because we have an inaccessibility of the entangled correlations with other systems. So in that sense, you know, there isn't actually, in some sense, a genuine entropy increase. The actual entropy increase looks like it's something happening locally, but as you move out, you find it sort of vanishes. And then, yeah, well, maybe we can live with that. Maybe there's a story we can tell and we can live with that. But wouldn't it be nicer if we didn't have to live with it? Okay, let's propose something else. Let's propose that it's not a mixture at all. I mean, in a sense, it's not an improper mixture. It's not a statistical mixture. But here we're going to form exactly the same formally density matrix, but the W's here are physical properties of this individual system, and it's not obtained through tracing out any correlations with the environment or any entanglement with the environment. You can have this completely isolated system, and no matter how much larger the environmental systems you include, it's not going to reveal any correlations or entanglements. Nevertheless, that individual system is going to be described by this density matrix, by this state. So I'm going to use this varo symbol whenever I'm referring to an Ontic density matrix, just to distinguish them. And that, you know, has the hurrah, entropy would be objective and fundamental. And this means we would be able to sort of say the Gibbs von Neumann can be an objective property of the system. Okay, the main problem with this though is it's not going to solve some of the key problems we really want to solve. Yeah, if we just continue with our regular Schrodinger evolution, then the Gibbs entropy, the Gibbs von Neumann entropy of such an ontic density matrix is going to stay constant in time. So all of the problems with the arrow of time are going to still be there. If we're going to look for entropy increase, it's still not going to give us explanation of entropy increase, and it's still not going to give us, unless we sort of look for the developing correlations or entanglement with the environment and trace out environmental degrees of freedom. And any attempt to explain entropy increase that way is going to encounter exactly the same problems looking backwards in time, that we're going to find that the same arguments are going to say entropy was higher in the past. So although this is, gives a real Gibbs von Neumann entropy, it doesn't actually solve the problem of the arrow of time, at least, which is perhaps one of the more pressing and puzzling problems in statistical mechanics. Okay, so it's indistinguishable from mixture. It doesn't increase in time, so it's not really doing the job that we actually want to do. It's good. It might seem like an advance, but it's not doing the job. So what I want to do is open up possibilities that this gives us that's going to fix even this. Row-ontic dynamics. So two of the properties above here is we've got the energy, it's energy conserving, and of course the density matrix itself, its trace stays constant. It has trace 1. But what we want is to modify it so that the entropy is increasing over time. And that's going to be a strictly increasing over time, both backwards and forwards in time. So if we have one of dynamics that we look forward in time, the entropy will go up. And we look backwards in time, the entropy will go down. So this is the thing that it wants to solve. It wants to cut out any need for initial condition hypothesis. The suggestion would be, if given, this is a dynamics that given the current state of the world, given the current state of a system, if it's in a sort of medium entropy state, this ontic density matrix, then yes, assuredly, this evolution will give us a higher entropy state in the future, but also assuredly, it will give us a lower entropy state in the past, just conditionalizing on its current ontic state. And there will be no further need for a past hypothesis. That's that would be the aim of this program. Whether it succeeds or not is another matter. And just maybe as a desiderata, in the similar way that when introducing collapse parameters, one of the problems we have to explain when introducing a collapse theory is how come the existing interference effects have been observed at individual quantum states. We need the collapse to not happen too fast. Well, for this kind of row-ontic dynamics, we need to actually be able to recover places where we've actually not seeing this dynamics. So places where we have been able to maintain pure states, we really want to actually keep pure states going. So maybe there's a desiderata that the entropy should stay 0 for pure states. Pure states will be mapped to pure states. That'll actually mean we can recover a lot of things we already know as well. Now that's actually a tall order to do. Fortunately, I don't have to do it because Gianpaolo Beretta actually did it for me, which I didn't know when I started on this research, but I discovered a few years later. So Beretta actually working in a very similar framework of trying to turn quantum states into operators and looking at the geometric picture of operator spaces, came up with a dynamic to fit those constraints. So the first step is taking the density matrix and saying, well, we can actually factorize this into this kind of square root density matrix formalism. And we can rewrite most of this is the straightforward Hamiltonian dynamics, the normal Schrodinger evolution. And we can just
is it possible to ask a question, or should I wait until the end? My question would be, the gamma, is that an operator or is it a vector?
It's an operator.
Okay.
At this point, it's an operator. It's an operator in the same space as the density matrices and the observables.
Okay, thank you.
There's a certain unitary freedom, by the way, in this setup when you do this factorization. That inevitably comes from this. Now, the proposal is to take this ontic density matrix and this square root of the ontic density matrix formalism, and simply take this previous evolution and add an extra term. And the extra term is going to do the job that we're looking for. but it has to satisfy a number of criteria. Alistair, are you asking a question? No, okay.
Can I ask another question? Should I think of the gamma also as ontic or not?
The gamma is ontic as well, yes.
Okay, good.
Yeah.
It's up to you, Owen, whether to take questions.
Well, I'm happy to take questions as long as they're just quick clarification questions. Yeah, maybe detailed long questions. I'm not sure how long this talk will take and how long I have. So detailed long questions maybe should be kept to discussion at the end. But I'm happy to take clarifications because I'm introducing a new formal notation here and a new formalism here that people may not be familiar with. So clarifications is perfectly fine. Yeah. So yeah, this is actually a new space, though. We can actually look at this because we're actually now defining a space of density matrices as being our space of states. And we now can look at we can now, in fact, then go onto this gamma space as a space of states. So now we have a parameterized path in this space of states, the square root density matrix space. We've got a tangent vector to the path. And we can actually define an inner product on this space. Now, an inner product on the operators in the space and the density matrices. And the reason why this is a rather cool construction is that now we get to use lots of geometric results because we have an inner product, and we can actually use a lot of results like this where we can actually now treat them as being vectors. So if we rewrite this with the inner product, what we can find is the rate of change of some observable along a path turns out it drops out into this form. Now the 2's there is because of the symmetrization. So, and it helps if we just start to try and think of these objects on either side of the dot as being now vectors, and it being a vector space, because we can now then just help ourselves to the geometric language. Whereas if, for example, this 2 gamma A is perpendicular to the path, then there's going to be no change of the expectation value of the property along the path. And if it's parallel to the path, we're going to get maximum change of the property as we move along some path in the space. And we're going to use that simple idea to construct an X term that's going to do our job for us. So we've got no change if it's perpendicular, max change when it's parallel. So the 2 constraints we really want is we want this to be an energy conserving evolution. And we do want the density matrix to stay as a density matrix and not wander off from being actually a kind of a density matrix state. So we have 2 conditions. Now it turns out this one is actually going to be automatically satisfied for the kind of dynamics we're setting up. So the main one we want to make sure is just that actually the Hamiltonian is going, the dynamics are such that this is going to hold as being 0 for the Hamiltonian. Well, again, looking at this in terms of as vectors formalism, with the easy way to think about this is to say we can take our 2 gamma S vector and we can break it up as being the subspace that's spanned by 2 gamma H and gamma, and the part of the subspace that's orthogonal to 2 gamma H and gamma, and we just pick out the part that's orthogonal to 2 gamma H and gamma. And that bit here, if we're using this is the direction with maximum change in S, in which is not going to change the normalization of the density matrix, and it's not going to change the energy of the system. So that's our candidate for X. We just add that in as our X, and we introduce a T. Now, that's
a quick clarification again.
Yes, sure.
Can you say again what S is?
S here is actually the operator corresponding to the Gibbs von Neumann entropy.
Okay. Mm-hmm.
Yeah, sorry, I didn't say that. You're right, and you're correct to pick me up on that. I haven't actually mentioned that. S is the Gibbs von Neumann entropy operator here. So we've just, by construction, picked something out that's going to go in a direction that's going to increase the Gibbs von Neumann entropy of the ontic density matrix without changing the energy or wandering off from actually having a genuine density matrix. So the construction is actually, rather neat in that case. Why did I have to go to this kind of geometric kind of picture in order to describe it? Well, if we actually try and look what it looks like under the normal way of writing things, it looks like that, which is a lot more complicated to work out. You can give an explicit construction for it in the normal way of doing it, but if you actually try and churn through it, it's considerably more complicated, and the expression, as you can see, is not the most transparent in the world as to why that works. And of course, it's got the Gibbs-1 entropy littered throughout here to make it work. But on the other hand, that entropy is supposed to be a physical property of the system, so it's not necessarily a problem that it's actually coupling to the dynamics now. This does introduce a new physical constant. I've said physical constant-ish because it's not required of this that this actually be a single constant that applies to all kinds of dynamics. Different systems might be able to thermalize at different rates. It's not even clear it actually has to not, it could actually be a nonlinear term itself. It could actually depend upon rho. But that gets very messy. It's neater if you just keep it as a constant. Bonus is for pure states stay pure states. So that means that all the results we have from quantum mechanics on pure states we can still rely on, at least. Now looking at this dynamics, this straight away we actually have some immediate consequences of it. So if we have an epistemic density matrix, now here we've just got uncertainty over pure states. Well, the pure states stay pure states. So our epistemic density matrix just sitting there left to its own will stay there as an epistemic density matrix and not change. If we have a completely ontic density matrix that is not nevertheless an equilibrium density matrix, and we let it evolve under this dynamics, then it will evolve assuredly into the canonical distribution, because it will work to maximize its entropy while keeping its energy fixed. And that's going to drive it in the direction of the canonical state. Rather more interesting is if we suppose we actually had a mixed state, a mixture of ontic density matrices. Suppose we had an epistemic uncertainty as to what the ontic density matrix was, then what would actually happen is that each of these ontic density matrices would evolve towards their own respective nearest equilibrium, which would keep their own individual mean energies fixed. But we would be uncertain. I think I've missed up a bunch of probabilities in here. Yes, there should be a set of probabilities here. And that means even if, for example, these three initial density matrices all have the same form and are all observably indistinguishable, then over time, they will become distinguishable. They will actually start to show different statistics. And that's something you can't get without using this rho ontic dynamics, because of the linearity trap of everything like the typical master equations that are used for density matrices, where you only have probabilities, and then you have the linear Schrodinger evolutions, or even with dynamic collapses.
I have another quick clarification question.
Sure.
On your slide, you have an equation for d gamma dt and an equation for d rho dt. And what I notice is that on the right-hand side of the equation for d rho dt, there's no gamma. So in order to compute d rho dt, I wouldn't have to know what gamma is actually. So after, could I take the equation for d rho dt as an axiom and just forget about the gamma?
You could. I think you could take this one as just being fundamental and the gamma as just being construction. There certainly is a unitary freedom between going between the gamma picture and the rho picture.
Okay.
So there's not so generally you'll pick you can pick a gamma representation. You've got a unitary freedom in that. You could certainly just go with the rho representation. The reason for preferring the gamma representation is entirely pragmatic in that it's a lot more compact, it's a lot easier to write down, and it's a lot easier to see why you get to this construction. Trying to get to this construction is really a lot harder if you're trying to do it from first principles. But yeah, that's purely a pragmatic consideration. You can certainly take, and there's an argument for taking the ontic rho as being the fundamental picture, and this is just being something that is a convenient calculational tool. But they should be completely consistent, at least when viewed that way. So the point there I was actually going to get into there is that this gives an empirically testable signature, which of course should be a lot of attention should be paid to, because whenever you can get an empirically testable signature of something, that actually allows us to start looking at it. It's an interesting empirically testable signature because it won't ever be shown up necessarily by looking at the statistics of an individual situation at one point in time. If I prepare a system and measure it, I won't be able to tell anything from that. The only way I can actually get this empirical signature is I compare systems as they evolve over time and see that these evolve in a way that these don't evolve. So that's an empirical testable signature. So I'm just going to emphasize that by putting it in red and bold, just calling attention to there's an empirically testable signature. Matter of fact, I'm actually going to put it even bigger and highlight it because, hey, look, we've got an empirically testable signature to this theory, and that's actually worth shouting about. Okay, I'm not going to spend much time talking about the measurement problem to this audience. But in a nutshell, we have the problem with quantum mechanics that linear evolution gives this thing which is not a simple statistical mixture, and yet what we observe is a simple statistical mixture. And the first division in responses to this, one is to actually take wave function is real and does represent the state of a physical object. And the second one is wave function doesn't represent any state of part of the world. And so the change from a superposition to a statistical mixture is something else. It doesn't have to be treated so much as something real. Obviously, given the nature of the talks we're having now, the second option really isn't the one that we're going to be terribly interested in. So broadly, the three strategies that people adopt in response to the first one, the wave function is real, is to see which of the trilemma do you drop. Linear evolution is right. There's no extra structure to the world. Both outcomes occur. Everettian in many worlds. Linear evolution is right, but there is extra structure to the world. Hidden variables determine which outcomes occurred. Linear evolution is not right. The state of the world is actually up or down. The wave function has collapsed by an objective physical process. And I'm going to look now just actually at how this rho-ontic dynamics interacts with those three results. I think in the context of Katie's talk, actually, it's saying this point of view is going to say that obviously is that statistical mechanical probabilities are genuinely quantum probabilities. The rho-ontic density matrix is a quantum object. So if that's the thermodynamic or thermal properties are coming from the rho-ontic density matrix, then the only source of probabilities in that are going to be quantum mechanical probabilities. So if this picture is going to actually explain thermal fluctuations and the probabilistic predictions of statistical mechanics, it's going to have to interact with the quantum measurement probabilities. Well, the first thing to say is if we stick with pure states, they evolve into pure states, and we haven't got anywhere at all. So we have to have at least some systems be in ontic density matrix for the first place before we can get anywhere. Can a little bit of impurity help with solving the measurement problem? Or a little bit of, impurity? Well, not really. I mean, if we sort of make these ontic density matrices and make them impure, they're just going to evolve into an ontic density matrix over here. This isn't going to be a statistical mixture of outcomes anymore at all. So even though these are actually, density matrices with non-zero entropy, this is not a statistical mixture because it's still an ontic density matrix. So that's not even remotely helpful for solving the measurement problem. In fact, it's made it even worse because at least when we have a collapse from the superposition, the entangled superposition to the statistical mixture, there is observable consequences of the collapse. Whereas here we've gone from a situation where we're saying there is an ontic density matrix, but it looks just like a statistical mixture and there's no observable consequences to it. So that's really not helpful at all. Okay, so onto dynamics is really not helping us solve the measurement problem. So we've got to go back. How do we look at how these three wave function realist approaches work? Well, we're going to have to see how each of these three approaches then tackle the rho-ontic dynamics. Obviously, the anti-realist solution to the measurement problem is just not even on the table for this because we're being realist about density matrices. Okay. So the many worlds, the core interpretation doesn't appear to change. I mean, we seem to have these ontic density matrices would now seem to actually encode the patterns of the different outcomes and would seem to be very different. So if one is convinced of the story that, for example, Sanders and Wallace and so forth and collaborators are told, then we seem to have a case where that you will have the branches decohering, evolving into their own separate branches with their outcomes emerging. So that doesn't seem to have changed too much. There is a slight worry, though, is that whether or not the probability interpretation can be sustained. There is a possible interaction here, is that if we have these two outcomes and we don't have, and these say have the same energy, then what actually can happen is that these probabilities will actually shift over to being more equilibrium probabilities. So what we won't expect to see is stable probabilities in different branches over time. We might actually expect to see, in the right cases, that probabilities will shift. And if we don't have stable probabilities over time, does the kind of the Deutsch-Wallace approach to probabilities still succeed? That's an open question. So I don't know if that's actually going to be a problem. There's another problem, is that the very fact that you've got these different branches, and this is going to be a generic problem, we're going to find out, but it's the first point we're encountering it. Branch-specific entropy could go down. So although we've got a rho-ontic dynamics that guarantees that the entropy overall is going up, what this tells us that if we take the entropy of the rho-ontic density matrix over all of the branches, that's got to be higher. But that doesn't tell us that the rho-ontic entropy on each sub-branch is higher. It could be that we're seeing in a measurement situation, the entropy goes down on each branch. That's a possibility. So again, the question of whether this happens depends on how the decoherence rate and the 1/Tor factor in the rho-ontic dynamics interact with each other and the timescales involved. So there's a worry here. We might get to objective entropy increases, but subjective entropy going down, and that really is, again, pulling in the opposite direction to what we would have wanted. So looking on to the next one, the Broglie-Bohm theory, for example. Now here we solve the problem by adding in particles having positions following trajectories. Now, would it be nice to actually have the Broglie-Bohm theory for an ontic density matrix? Well, fortunately, someone's already done that, so that's good. So here is basically, it's quite easy to generalize this to an ontic density matrix. You just take these W's as before and take them very seriously, and then in place of the Rx, you use this rho x, which you construct by weighted average. And if you do it right, you can find that the probability current manages to get the gradient of the phase in there. But this isn't a statistical average. And that's the most important point. This is not a statistical average of different phases. This is just one expression that is the probability current, or that is the current that drives the de Broglie-Bohm particles. So you can construct a trajectory interpretation for ontic density matrices. Will this work with the rho-ontic dynamics? We'll have to actually add this on top of the new equation. Now, the first thing to note is that we need a locally conserved probability current to get the de Broglie-Bohm theory. Conventionally, we need a locally conserved probability current to get the de Broglie-Bohm theory working, local in the configuration space. Well, there has been some work on making sure that the rho-ontic dynamics maintains no signaling theorems. So working with many body problems as generalizations, we have to work on, there is a entropy producing dynamic for each object in the equation. So it gets more complicated, but it certainly looks like there's the right kind of equations there that the ontic density matrix can be given a trajectory interpretation. It might be better to move on to something else where the actual entropy production is taking place as a field rather than attached to individual particles. But this is a technical program as to what would be the best solution to take in this case. Fundamentally, there seems to be no problem with having a trajectory interpretation of the rho-ontic dynamics. There is still a problem in the measuring situation, though, because this is a also sits within the no collapse situation where you're going to get branch specific entropy can go down. So when you have a measuring situation, just as this is not just a problem for Everett, this is a problem to Bohm as well, naturally, the Everettians would say. When you have a division into into different measurement outcomes, if those different outcomes have a lower entropy, you're going to get a perspectival reduction in entropy. So that's a kind of worry. Is this going to pull in the opposite direction? The most interesting interaction, how am I doing on time, by the way?
We've got about 6 or 7 minutes left in the official session. We started.
Okay. All right. Okay, I'm nearly finished then. That's good. Okay,
if you could wrap up within, say, 5 or so minutes, that'd be perfect.
Right. Okay, fine. So the most interesting interaction with the dynamic collapse in some ways, because this is the solution that also says let's modify the dynamics in order to solve a problem. So looking, for example, at the CSL equation, the continuous spontaneous localization equation for collapse. I mean, this is set up with, say, a matter field to localize wave functions within the matter field so that objects tend to become localized and clumpy together. So we end up with well-localized objects. We can put that into a master equation format for the density matrix. And the effect of that equation is the tendency to diagonalize this density matrix in the basis in which objects have well-localized positions.
Quick clarification question. The gamma here is different from the previous gamma.
Oh yes, this is annoying. I've just taken this gamma out of obviously the classic Bassi and Girardi paper, and because that's the notation they use. But this is a different gamma, and actually, as I was preparing the slides this morning, I was like, oh no, it's too late to change it.
Is that just a constant?
I think that's a constant, yes.
Giving kind of the strength of collapses.
Yeah, I think that is yes.
Okay.
That's the constant. I mean, this is just the CSL master equation. Yeah, this is nothing of me. This, yeah, yeah. This is pretty much lifted straight out of Bassi and Girardi. Yeah. This equation, yeah, it has the advantage that because of the way the individual dynamics work, when we have a density matrix here according to dynamic collapse, and it diagonalizes in this basis in which objects have well-defined or pretty well-defined locations, we can actually make effectively, for all practical purposes, a ignorance interpretation of the density matrix where we can actually regard it as being a statistical mixture of the eigenstates of the density matrix, more or less. Now, if we were to just drop an ontological density matrix in there, it goes horribly wrong. The mass density doesn't localize because it's just actually the mass density. It's not a statistical mixture of localized wave functions in different locations. It's just a mixture of an ontic density matrix which has matter all over the place in all of the possible outcomes. So if we were to just drop the ontic density matrix into the CSL master equation, it would be a catastrophe. It would just completely fail to solve the measurement problem at all. So that's not the solution. So you have to actually go back away from density matrix and go back to the original collapse type program and say, well, look, okay, we can make it work with the collapse program. Go back to the original localization operator and build back up from the ground. So we have a random chance of a spontaneous collapse taking place. This is a different tour, just to clarify as well, Roderick. Again, I'll get in there first. It's a different tour. Okay. Now here we can still apply the localization collapse of the GRW to the ontic density matrix. And we have a localization operator. And that will work, and that will make things tend to localize. It's interesting to note that because I know this issue, if we take a statistical, this is going to be a stochastic process. So over time, we will get a statistical mixture of ontic density matrices. There is no equation for how this evolves. There is no master equation for the evolution of the statistical mixture of the density matrices as such, in general, because this will not obey any kind of master equation of this form. You need to come up with a new sets of equations that look at probability distributions over density matrix spaces to actually try and understand what's going on in this case. You then also have the problem we noted before with both the Everettian and de Broglie that when you have the outcomes could have a lower entropy. In this case, it's actually the entropy is decreasing objectively as well. It's not just merely the perspective of someone who's actually on a particular branch or a particular outcome. Okay, so in conclusion, to wrap up, if we take the idea of an rho-ontic density matrix as an opportunity to modify the Schrodinger dynamics, to actually sort of build in something more fundamental, to eliminate the past hypothesis altogether from our things. This really kind of pulls in a very different direction to the solutions to the measurement problem in several important ways. The ontological density matrix and cell equation won't localize. Collapse and no collapse theories will see decreases in the actual density matrix entropy, which goes against the objective of the rho-ontism in the first place. There's this possibility, it's still, I'm not sure, that this may undermine arguments on how to understand probabilities in many worlds. And it can't avoid this problem. You can't ignore it if this is the route you want to go, because as noted, the probabilities in statistical mechanics, if you take this kind of rho-ontic dynamics, have to come from quantum probabilities, because there's no other source of probabilities now. So you have to actually solve the measurement problem to be able to solve the problem of thermal fluctuations. However, it does cut both ways, because given if I'm putting this option on the table and saying out there, well, there's actually this possibility and it has an empirically testable signature, if we were to actually perform the experiments and actually find that rho-ontic dynamics had some validity, that could also radically push back against some of our interpretations of quantum mechanics and force us to revise some of the pictures that we have. Okay. Like silly cell, though, ultimately it makes novel empirical predictions. So ultimately, it is experiment that's going to have to decide which way that's going to go.